All right, hi everyone. Welcome to week 5. We're going to start off with a discussion of logical truth and tautology. Okay, if we start with the notion of possibility, the basic idea is that it just can be so. And this is a special kind of possibility called logical possibility, which is more expansive than mere physical possibility. So although it's physically impossible to travel faster than the speed of light, it's not logically impossible because it doesn't entail a contradiction. You can certainly imagine people traveling faster than the speed of light, and you can write a novel in which people travel faster than the speed of light. But you can't write a novel in which cubes are not cubes, because that's just not a logical possibility. Necessity, on the other hand, deals with what must be the case. And a special class of necessity is tautologies. There are whole logics that deal with possibility and necessity in terms of truths, and these are called modal logics. They're actually a lot of fun, and they're very interesting, and I've always really enjoyed them. But you need the basics that we do in this course in order to go on to do those. So there is dessert, but you have to eat your vegetables. Now, tautologies are a special kind of necessarily true sentence, and these are ones that are true in virtue of their logical form. We're going to see how this works using truth tables in just a minute, but first I'm going to jump to the board just to give an overview of the relationship between these notions of necessity and tautology. Let's make a quick Venn diagram to see the relationships between tautologies, logical truths, and then truths that are just necessary in virtue of limitations placed on the blocks language in Tarski's world. For starters, though, I want to give a Venn diagram with some more familiar concepts so we can just see how this works. Here's a Venn diagram which shows us that all Dalmatians are dogs and all dogs are mammals, but it doesn't work the other way around. So not every dog is a Dalmatian, although every Dalmatian is a dog, and not every mammal is a dog, although every dog is a mammal. Turning then to tautologies, logical necessities and so forth, we can see that every tautology is a logical necessity, but not the other way around, and every logical necessity is a Tarski's world necessity, but not the other way around. Here's what I mean. At the middle go our tautologies, which are true just in virtue of their logical form, which is to say they're connectives. So for instance, P or not P is a tautology, so is not both P and its negation. Moving outside of that, we have logical necessities. For instance, A is larger than B and B is larger than A. Those can't both be true. So for instance, take the Statue of Liberty and me as A and B. Now, the Statue of Liberty is larger than me, that's true, and it can't also be that I'm larger than the Statue of Liberty. Granted, maybe we could shrink down the Statue of Liberty so that it is smaller than me, but then the other conjunct comes out false. So if something is larger than something else, then that something else isn't larger than the original thing. This is necessarily true, but it's not a tautology because it's not a matter of the logical form. Outside of that, we have Tarski's world necessities that are not necessities and not tautologies. For instance, A is a cube, or it's a dodecahedron, or it's a tetrahedron. Now there are other shapes in the world. A could be a sphere, but there aren't other shapes in Tarski's world, and so this is a Tarski's world necessity. Now if we want to show that something is a tautology, we can do so by dropping it into a truth table. This is akin to the A or not A that we considered in a previous lecture. And if you want, you can run through the De Morgan's equivalences to see why it's actually the same thing, although expressed differently. Let's drop this into a truth table. Now this sentence only has one subformula, and so we only need one range of possibilities, which is all the ways that A could be either true or false. So there we go. Now we can start filling out from underneath here. So let's first show not A. We'll flip the true and false for A, so it'll be F and T. And A will be just the T and F over here. Now the connective is AND, which requires that both of them be true, so it'll be false in the first and also false in the second. But the main connective is this negation sign here, which flips the other one so that we get two T's. This sentence is therefore a tautology because it has all T's in the column under its main connective. Let's consider a slightly more complicated one. It might be relatively easy to see that this is a tautology, but let's drop it into a truth table anyway. Now here we have two letters, A and B, so we'll need to put both of these and all their combinations into the leftmost column of our truth table. The way I do this is to just do TF on the rightmost one, and then TTFF on the left, and then we would quadruple these if there were a C, as we'll see in just a moment. Filling these out then, not A or B is true in the first instance because B is true, but it's false in the second because B is false and A is true, so the flipped value of A is F, so both of them are Fs. It's then true because B is true, and it'll be true because, again, we get the opposite of A here, which is false in the bottom row. The next one, we get true in the first because A is true, true in the second also because A is true, false in the third because B is false, since B is true in the leftmost column, and the negation sign here flips the value, and true in the last because not B is true. Now our main connective here is the OR sign, and lining it up underneath the OR we have T, 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 T. Here's the intuitive idea. With A and B arranged like this, we have every possible combination of A and B. If every possible combination of A and B still results in true, then the sentence is a tautology. This is why we can use truth tables to show that sentences are tautologies. Let's consider one more that's more complicated than these two. I don't know about you, but I can't tell by looking at this whether or not it's a tautology. So we'll put it in a truth table. Now we have three letters here to deal with: A, B, and C. In general, the number of rows that we'll need is 2 to the power of n, where n equals the number of letters. So 2 to the power of 3, in this case, equals 8. So we'll write these all out. So I've written under C alternating true, false, and then under B I'll write 2 truths, 2 false, and repeat that. Finally, under A, I'll write 4 truths and 4 falses. If you prefer to do it in the other direction, you can take one letter and write half of them as truths and half of them as false. Then the next letter will be the first and third quarters truths and the second and fourth quarters false, and keep working down until you're at your last letter, which just alternates TF, whichever way works best for you. I'm going to work from the right-hand side over to the left here. B is going to be pretty easy because it's just going to be the same as B in the first column. So it'll be 2 truths and 2 falses and 2 truths and 2 falses. I'll do the same for C. I can just compare the B and C over here, so I don't think there's any point in writing out B again under this B. So this comes out true right here. False in the second because C is false. False in the third row because B is false. And false in the fourth because they're both false. True again in the fifth. And then false all the way down. Now we move on to not A. This will just be the opposite of the truth values of A in the leftmost column, so we get 4 falses and 4 truths. Now we've got either not A is true or the conjunction of B and C is true. So this is true in the first and false. So just to make clear, what I'm comparing here is the not A with the main connective of this subformula B and C. That gets me this main column here for this subformula, not A, or in parentheses B and C. I want to compare this line now with the one under the and. So what I'm comparing here is the A line and this column right here. And it's true just whenever they're both true. So true, true, and the rest is false. Now negation flips that, but notice that the main symbol here is this disjunctive sign. So we're going to compare ultimately this column right here with B. And it's disjunctive, so anywhere there's a T in either this left column or the B column, the whole thing comes out true. And there you have it. One straight column of T's all the way down under the main connective. Now, some people were asking about how to find the main connective. It's the one with the least parentheses around it. That's the most straightforward way of thinking about it. Notice, however, that or and not both have 0 parentheses around them. So what do we do here? Well, in that case, a binary connective trumps a unary connective because the unary connective is just bound to this whole subformula on the left. And so the main connective is just the or. The main connective is the one with the fewest parentheses around it, And a binary connective beats out a unary connective if there is any contest between them, as there is in this case. Now you might wonder, what about conjunctive strings like this? We can write these just fine, but technically we should write them with parentheses around them. And there's a straightforward way to just apply these. You just cluster them around the left. So you put parentheses around this first disjunct, then parentheses around the second one, and so on. And the same applies for conjunctive strings like P and Q and R. I want to consider one last notion before we wrap this up, and that's the logical possibility that we started everything off with. Recall that what's possible is what can be. And the way to show this is just that under the column of the main connective, there's at least one T. So for instance, take the subformula from one we considered earlier, B or C. Putting this in a truth table, we can compare the B and C, which we know because it's a disjunction comes out true in case at least one of them is true. Well, we have T values here underneath the main connective for at least one, in fact 3 cases, and that's all we need to say that something like this is possible. So if it's possible, it has at least one row true. If it's necessary, and if it's a tautology, it has to have all of them true. And that's how we can show that something is a possibility or a tautology using our truth tables.